Hello and welcome back to our plasma survey course. Today, whenever you're watching this, is lecture 9, and we're going to pick up from where we left in lecture 8. That was the discussion of what is called the polarization drift. We did derivation using vector algebra. That was a little messy, sorry about that. And now we're trying to repeat the derivation using the equation of motion for our charged particle. And let me remind you of where we closed lecture 8. We had written the equation of motion for the particle in the same way as we did for the motion without any electric field, the same way as we did it for the E cross B electric field, by taking derivatives of the two components of the momentum equation with respect to time and combining them so that we get equations that only involve the one of the two components of the velocity itself. Okay. Now, here is the equation for dx, omega c over b times dEx dt. Let me remind you here, I'm assuming that omega c, I'm defining omega c to be the absolute value of omega c, and therefore to be strictly larger than 0. Of course, assuming that the magnetic field is not 0. And then for the y component, I have similar equation. Second derivative of y with respect to time is equal to minus omega c squared vy minus, messing up my omegas, I'm sorry, minus omega c squared ex over b, where ex is a function of time and only of time, even though I've marked this derivative as a partial derivative. Just because in the general case, there may be other dependencies in Ex that we will need then to include in our derivation. Now, here is another interesting step that is very representative of how plasma physics works. So this is a little messy. We have a lot of different pieces, but we can make assumptions on the quantities in the system. Now, I want to emphasize what we mean when we say we can make assumptions. I'm going to assume that the time variations of the electric field are slow with respect to the gyration period. They happen on time scales that are longer than the gyration period. Is that assumption justified? Well, it's going to depend on the situation. But the way I'd like to think about this, and the way I encourage you to think about this, is that I'm really asking the question, if the time variation of the electric field is slow with respect to the period of gyration, the duration of a circle, of my charged particle around the magnetic field, how much can I say about the system? In yet another way to say this is not the most general way of solving the equations, but it's the way we can get to some result. And incidentally, not accidentally, it is actually relevant to the motion in fusion experiments. And therefore, it is a useful result. Okay, then, what do we have? First, I already said, maybe I can put that in official writing. The time variation of the electric field, I'm just going to write E, is slow with respect the gyro motion. Anything else? In fact, yes. I'm going to make an assumption on the E cross B velocity, and I'm going to assume that it is of the following order. Maybe I need a little more space here. We'll make it work. Okay. My V equals B. Well, let me just use the absolute value. So I'll do without the vector on the velocity itself, is of the order of K, just typical scale length for my system, times Larmor radius. So I'm sorry. K, typical scale length of in the system times Larmor radius times the velocity of the particle. Obviously, the quantity K times R sub L is dimensionless. So that's my ordering. In other words, it is the E cross B velocity is small in this specific ratio. Then this may take a little convincing, but you should be able to see that the second term in on the right-hand side of my equation on top is actually second order in this expansion parameter. This hopefully will be clear. So because of the assumptions I'm making, E over B is of higher order than the velocity itself, and omega c is of higher order. The derivative with respect to time is of higher order than omega c. So that gives me two orders with respect to omega c. And while this term is of order 0, this is of order 2. What about the ones I have down here? Well, this is the same as the one before. And this one, you should remember, but you should also see it. E over B gives me one order down. with respect to V. So that's of order 1, and that's the piece that will give me the E cross B velocity. Then now we need to go to second order. In other words, solving this equation order by order, at the 0th order, we get the gyration motion, nothing else. At order 1, we get the E cross B drift. At order 2, we are going to get something new. That's not so new because we saw it in lecture 8, but something that was not contained in the calculation, as we have done it this way, not contained in that calculation so far. And again, the ordering is in time derivatives with respect to the gyration motion. Okay, then so what we need to solve now is the second order of the equation on top of the first equation. Maybe let me put numbers to these equations, 1 and 2. And let's look at the second order in time of my equation 1. That's going to give me the following equation. Now let me write it first. And then I'll speak to it for a moment. Hopefully this should be clear enough, but just in case. Okay, second derivative of Vx2 with respect to time is equal to minus omega c squared Vx2 plus or minus omega c over b. Did I copy it right? Yes, okay. dx dt. Now, this is an equation that I need to solve for, obviously. The velocity but what I want you to keep in mind that Vx is equal to Vx0 plus Vx1 plus Vx2, where each additional number, that is 1 with respect to 0, 2 with respect to 1, means that this piece of the velocity is 1 order smaller than the previous one. And we've already encountered all these pieces. Let me see how I do if I do it blindly. Okay, what are these pieces? First one, or the 0th order, is the gyration motion. The first order is the E cross B drift. The second order is going to be what we're trying to calculate, the polarization drift. It's a new piece. Okay, then, but you may see a problem. We're looking for a constant. Well, assuming that the time derivative of the electric field is a constant, we should also obtain a constant velocity in our solution, but we have time derivatives of that solution, or that is of v sub x2. One way out is to assume, well, that velocity is just going to be a constant, which is a pretty strong assumption. But there is an easier way, well, may not be easier actually, but it's definitely more elegant and more like what a physicist should do the calculation properly. What we're going to do, I'm going to take the average of this equation, let me call it 3. No. Over, okay. Over, no. Okay, I'm going to fight with this for a moment. This is extremely annoying. Okay, gotcha. Over a duration period, just to make things more neat, it is even better to take that average over many duration periods. Then I realized that the time derivative of my velocity, the one velocity I'm trying to calculate, v sub x2, is going to have two parts. I can break it into two scales. There is a fast varying part, which is varying over the duration period, and there is going to be a slow varying part, which is whatever is left once I take out the part that the part that corresponds to the duration motion. Well, if I do that, that second piece of the time derivative of vx2 is going to be of an order lower. I may have to think, is it 1 or 2 orders lower? It doesn't matter. It's not of the same order. It's lower in order, and I can throw it away because it is lower in order than the piece that I'm averaging out. But if what's left after this average operation is smaller than order 2, then I can neglect it in my equation. Then I only have one little piece left. And that piece is what we're going to write next. Vx2, I'm just going to solve. My equation is going to be equal to 1 over omega b times d dt. And notice that if I do the same thing with my second equation up here, the one for Vy, I get Vy equals 0. to this order. If I take the average, the only surviving term is the average of Vy over the gyration motion, and that's to second order 0. Okay, well then, great. We have pretty much solved our problem. That is our, oops, the wrong color. That is our polarization drift velocity. Now, if you remember what we did when we got started, we assumed that the magnetic field was in the z direction, out of the screen or page or whatever, and we picked x as the direction of the electric field, which was in the plane perpendicular to B. But our calculation would have worked regardless of what the direction of the electric field was on the screen we're looking at. In other words, our derivation is actually more general than just the case where the electric field is in the x direction, as I now added to my equation. And therefore, I can write it as follows, and I'll put this in writing so we're clear about what I'm doing. Oops, sorry. What's happening? I lost my quotation mark. Sorry about that. Since the x direction is arbitrary, then in general, I obtain the result, which is the result I was looking for, that V, now not x, but perp for the 2 is equal to, oh, I lost a plus or minus. I'm really bad with science, or I have been in the last couple of days. Sorry about that. Okay, plus or minus 1 over omega c times B times dE perp now dt, or recalling the definition of omega c and recalling that I'm setting omega c to be the absolute value of omega c, therefore using the absolute value of the charge, I can remove that absolute value and take into account the sign of the charge, and that's going to take care of this plus or minus that keeps bothering me. Our polarization drift velocity, which is again of order 2 in our expansion over time scales, looks like this. And here I'm just going to put the total derivative of the perpendicular field with respect to time under the assumption that that field does not depend on space. Okay, that was a bit of work. And it's a few things to note here now that we finally got this result. But first thing, the velocity is in opposite directions for ions and electrons. There is a charge without the absolute value. Also, the velocity may be good to type these things so we don't lose track of what is important. as I was saying, opposite direction for ions and electrons. It depends on them explicitly and linearly on the mass. Therefore, it's dominated by the ions. Thirdly, as a consequence of point one, this is going to create a current. Which, with some imagination, or maybe not so much, we are going to call the polarization current. Okay, that was a bit of work. It took us some good amount of time over a couple of lectures. But this gives us, again, one more idea, one more feeling for how complicated plasma physics can be. We're just looking at the motion of a single particle in a pre-assigned field that the particle does not modify, and we're assuming slow time variations of the electric field, which is straight, constant in space, and the magnetic, and it's perpendicular to the magnetic field, which is also constant in both space and time. And this was quite a bit of work to get to this result. Still, this is something that we can obtain explicitly, which is always a good and happy thing. Okay, to this point, we have learned, hopefully, we have learned, but at least we have talked about a lot of things, considering the motion of a single particle in a magnetic field, with or without an electric field, with or without time variations, space variations, and so on. This is not the end of the story. There is definitely more that can be done, but hopefully by now you're getting the general idea of how to proceed in this type of problem. I'm not going to go in detail, or will never be done, into some of the other drifts that can be written. I'm just going to very briefly sketch the treatment of decays with space varying or space dependent. Let's see. Electric field. And I should mention that this is an effect that only occurs if we keep track of the fact that the Larmor radius is finite. Now, FLR is something that you will likely encounter in your work on plasma physics. Of course, it depends on what you do. This may not be relevant for your specific research, but in general, FLR stands for, as I said, finite. Finite Larmor radius. Now, let's see what that means, and that this is the reason why I'm going to briefly go over this piece, even though we're not going to really do the calculation in detail. What finite Larmor radius means is that if I look at the motion of the particle and not just at the motion of the center of gyration, but what varies over a gyration orbit, not what varies in time in this case, but what varies in space, I may find that some lengths over that length that corresponds to the size of the Larmor radius, my particle experiences variations of some relevant quantity that will then make things different in some way. Okay, is this terribly confusing? Maybe. Do you remember what we did for the grad B drift? Well, that's a finite Larmor radius effect. The particle can only see that the magnetic field is changing in space because over a gyration, that is over the distance between the two sides of the orbit, it sees different values of the magnetic field. If the Larmor radius was exactly 0, the grad B drift wouldn't exist. And pretty much the same thing happens for non-uniform electric field. It works out in a very analogous way. So let's see how that goes. Very well, then. Let's do this way. We're going to start from the equation of motion for our particle. M dv dt is equal to Q times E plus V cross B, where now the electric field depends on the position. Then I'm going to do what we just did for the polarization drift. I'm going to take the average over a gyration orbit, which is often indicated with the shortened expression of gyro average. Okay, let's see if I can remember how many equations I've numbered. I think only 3, so this should be equation 4 for today. No, don't hurry. Sorry. 4. Very good. And let's make this green. Standard colors. Thank you, green. And let me call this equation 4. Okay. Let's see what that looks like. I'm going to oops, I wasn't done. I'm going to take the gyro average of that equation. Oh, sorry. I forgot. Okay. And now in black, I'm going to assume the usual form that we've used for drifts for my velocity. That is that V is equal to a drift velocity plus V0, which is just the gyration motion, where the drift velocity is assumed to be a constant. Again. Okay. Then taking my average and skipping some steps, I get on the left-hand side m times the average of m times the derivative of the drift velocity is going to be equal to the average of q times E plus V cross B or Q times E plus V drift. Oops, sorry. The average of E, so let me use the same symbol. Average of E plus V drift cross B. As usual, I'm assuming that B doesn't change, and this is going to be equal to 0. Then this is trivial at this point. We know how to do this. V drift is the average of E cross B divided by B squared. Great, but what is the average of E? Well, now here's where things get interesting. I keep saying that things keep getting more interesting. What can I do? All right. what tools do we have at our disposal to calculate that average? Well, we can do the Taylor expansion. We've done similar things before, so we know how to proceed. E is going to be, let's see, I'm just going to write approximately equal, and I'm going to center my frame of reference at the center of on the gyro center, so that I don't have to keep track of any other coordinate. So I'm going to have E0 plus R dot grad E plus x squared over 2 second derivative with respect to x squared plus y squared over 2 second derivative with respect to y squared plus let's do it this way. It's going to be interesting. All right, I'm going to pause to write, to type this. And I erase half of my x squared here. Okay. Hold on for a moment and we'll type this. Okay, here we are back. I have the second derivative with respect to x divided by 2 times x squared divided by 2, the second derivative with respect to y times y squared divided by 2, plus the cross term, that's dx dy pieces applied to E. And I'll show you in a second why I don't need the rest. So I wrote approximately equal, so I don't need plus anything else. Now I take this expression, I take my average, I need the average of E. Here is another word that plasma physicists love. The average is going to, the average of a linear quantity of an odd quantity is over a period is going to be 0, and that applies also to the cross terms. And that is the reason why I needed to keep my derivation to, sorry, my expansion, Taylor expansion to second order. Putting the pieces together, the average of the electric field over a gyration is E0 plus Larmor radius square over 4 times del square of E. And my modified E cross B drift is going to be given by 1 plus Larmor radius square over 4 times the second derivative, that is the del square of E, and I'm going to put everything on the right-hand side of, or on the right of my second derivatives, since I'm assuming, as usual, that the magnetic field is a constant. I'm only changing one field at a time. Okay, that's the modified expression for my E cross B drift. I know I did this quickly. I just want to give you an idea of how this type of work proceeds. What you do is look at variations over the scale length that corresponds to, if you're looking at FLR effects, to the Larmor radius. And in this case, we can do that in a relatively simple way by taking a Taylor expansion, which, don't forget, is in 2 dimensions. And we notice, doing the calculation, I jumped the gun more than a little bit, but doing the calculation, you notice that linear terms are going to be averaged to 0, and therefore you need to keep higher order effects. Fortunately, second order effects do not average to 0, so that's where you can stop. Now, the interesting result here is that for this drift, the E cross B drift, the FLR effects come in to second order in the Larmor radius. But those are going to be pretty small. The second derivatives that are in my del square are going to be over scale length that are much longer than the Larmor radius. So this effect is going to be, under the assumptions we're using here, pretty small. As I mentioned earlier, we could keep going a little bit longer. Maybe I could write you a summary or something like that, but let's switch gears and let's jump to a different topic. I'm just going to let me call it treatment, not mechanics. Oops. What I want to look at next is how a very powerful tool that we learn in classical mechanics, that is the Hamiltonian formulation of classical mechanics, can help us in plasma physics. I'm going to follow pretty closely the textbook here, but I'm not going to go into any depth, really. We'll just look at the general idea, an example, and maybe a little bit more. I doubt will be done by lecture 10, but let's try not to spend too much time here because there are so many other fascinating things that we need to touch on. This is a very powerful method, but a proper treatment will take an advanced course by itself. So we'll just lightly touch on it. Okay. First thing I'm going to write is a few general letters, non-random. I'm going to use the letter L to indicate my Lagrangian. And I'm going to use this symbol to indicate the Hamiltonian. Hamiltonian without a final A. Okay. And you know from classical mechanics that I can relate the two through the relation at H. Hamiltonian is going to be equal to the sum over the coordinates I q dot I times pi minus L. Other textbooks will use subscript and superscripts. I'm not going to worry about that level of detail. I'm just going to indicate the sum over I, whereas you recall from classical mechanics, I'm going to use Q to indicate generalized coordinates. And I'm going to use the symbol lowercase p to indicate generalized momentum. Where the same index corresponds to the same coordinates, that is the generalized moment p sub I is conjugate to the generalized coordinate q sub I, where the coordinates could be anything, do not need to be spatial coordinates. Now, it turns out, not surprisingly, I've already hinted at this, that you can do a lot with this method. The catch is, what is the Lagrangian for my system so that I can calculate the Hamiltonian? I'm not going to go into the discussion of how you get this Lagrangian. You may have seen it already in other courses. If you haven't, I'm just going to state the following, that the Lagrangian for a single particle in an electromagnetic field looks as follows. It's got the kinetic energy, then a term q a dot v, and a term minus q phi, where a is the vector potential, that is b is equal to del cross a, and phi is the scalar potential defined by E is equal to minus grad phi minus dA dt. Then you know all these things already again. Then once you have decided what your generalized coordinates are, you can calculate the momenta from the Lagrangian, taking the derivatives with respect to q dots. Here the dot is invisible. It's a bit of a mess here. And I just made it worse. Okay. Sorry about that. You know how this goes. You will not be confused, but still, I should write it correctly and in a readable way. Okay. Then you can write the Hamilton equations. Q dot I is equal to dh. Sorry, I'm not using that h. dh dpi, and p dot I is equal to minus dh dq I. And also, you'll know that the time derivative of the Hamiltonian is equal to minus the time derivative of the Lagrangian. Okay, things you already know. You get 2n equations. If you have n degrees of freedom in your system, or at least n coordinates in your system, you may have fewer degrees of freedom than the number of coordinates, but you can still write the equations. Then you'll just get conserved quantities. You know that there is some freedom of gauge choice for your potentials from ENM, and you also know what the requirements are. What does it mean for H to be conserved, and when H is equal to the energy? All of those things. I'm mentioning things quickly to remind you of things that you already know and to emphasize the fact that all of those things that you have learned in classical mechanics actually have a value and an importance in here too. You also know that if the Hamiltonian does not depend on a certain coordinate, then see. Then the partial derivative of the Hamiltonian with respect to that coordinate will be 0. Then it follows that the momentum, to generalized momentum associated with that coordinates has a 0 derivative. That's its equation. You see it from the top there. And therefore, Pi is a conserved quantity. That is, if you prefer, it's a constant of the motion. Okay, so that's a brief reminder of all these things that you already know from classical mechanics. And this may be a good place to stop since we're at about the hour mark. And we can go over the examples that are in the textbook in lecture 10. In fact, we're, major spoiler, only going to talk about the axially symmetric magnetic mirror field. We have already discussed mirror motion, even though not in great detail. We'll go over it again using the Hamiltonian method, so you kind of see it twice, and you can have a flavor of how the Hamiltonian method works. But that's going to be next time. And until then, please keep enjoying the course. Bye-bye.